Okay, good afternoon, everyone. Am I audible?
Yes,
Okay, so today is the fifth week of interaction session of reliability-based structural design. So, uh, today, what we will do, we are at actually module reliability, first order reliability method. We are solving first order reliability method problems using Rackwitz algorithm, and on the last interaction session, we have you know solve some uncorrelated normal problems related to your limit state function. And today what we will do, today we will go through that four possible cases where random variables in the limit state can be correlated, can be uncorrelated, can be normal, or can be non-normal. So first we will go through that four possible cases, and we will make one generic function file, that of generic function file of Rackwitz, as well as we will make a generic function file for Rackwitz-Fiessler algorithm to solve that first order reliability problems. So first let's go through that four cases, then we will make one generic function file which can handle that four possible cases where your limited function can have different kind of random variables and their nature can be different. Okay, so let's quickly start. Okay, so basically today we will solve problems using MATLAB, and we will make that generic function files like which can handle these four kind of problems uh, for Rackwitz as well as Rackwitz-Fiessler algorithm. And we will see what is the difference between Rackwitz and Rackwitz-Fiessler algorithm. Okay, so let's revisit that Haushofer-Linde reliability index quickly, because we are solving the reliability uh, problem using the definition of Haushofer-Linde. Okay, so what was the definition? It was nothing but the Haushofer-Linde reliability index. What that definition says, that if we have a limit state on the standard normal space, then the reliability index is nothing but the optimal distance from the limit state function in standard normal space to the origin. So if we have a nonlinear function, we have seen that it's nothing but an optimization problem, and we solve that problem using Lagrange multiplier technique, where we have that constraint condition that gz equals to 0. That means all the design points should lie on that limit state on standard normal space. And we have found out that final optimal solution, that z star will be nothing but alpha star into beta. Alphas are nothing but the direction cosines of that point and multiplied by reliability index. Okay, and we have solved problem using the Rackwitz algorithm. And how that Rackwitz algorithm works, we already have seen it, though we just go through it quickly. So first, what we need to do, step one, we need to transform our limit state into standard normal space. And we can easily do that, like we have the equation like x1, or if we want to convert that x1 into z space, so just we need to subtract that mean of x1 from x1 and divided with x1, we will get the random variable in standard normal space. So if once we have that random variables in standard normal space, we can write the limit state function in standard normal space. Now once we have the limit state function in standard normal space, we need to evaluate the gradient of that uh, limit state function in standard normal space, so that we can evaluate the direction cosines. And then we have seen that we need to assume some initial values of alpha and beta. That is our starting point of the optimization. And then once we have the initial betas and alphas, now we can and construct that uh, equation of the standard normal space, or the equation of the limit state function in standard normal space in terms of beta and alpha, and we need to solve for beta. Once we have that new beta, again we need to find out the new alphas, and this iteration will continue until we get some convergence. Convergence means we need to set some tolerance limit between two successive betas. Once we get that tolerance limit, that iteration will stop, and we will get that final beta and alphas. When we get that final beta and alpha, So we can get the design points on the standard normal domain. So z1 is equals to alpha 1 into beta, so on z2 is equals to alpha 2 into beta, and so on. And once we have that design points on the standard normal domain, we can then convert back into actual domain. Like here we have converted into standard normal space. Now we can easily find out x1 is equals to nothing but that sigma into z1 plus mu1. So by this way, we can convert it back into our original domain, and we will get the final design points with respect to that probability of failure and that beta value. Okay, so that was the standard procedure, and this was for normal random variable sorry and uncorrelated case. That means no correlation was there in the limit state function between the random variables, and all the random variables were considered as normal random variable. Right now we have seen that our limit state can have that four possible kind of combination of random variables. Like for this cantilever beam, if we have a limit state like g of x is equals to x1 x2 minus x3l. So here we have three random variables, x1 x2 and x3, right? Now that x1 and x2 can be normal, 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 and they can be uncorrelated. That means no correlation was there. So that was the first case. Now out of the three random variable, maybe one random variable is log normal. So if that case is happen, how we can counteract it, we need to see. Now if you know there are log normal random variable along with normal random variable plus some correlation are there, then what should be the case? So out of this, we have found out that four possible cases can be there. First, uncorrelated normal, then uncorrelated non-normal, correlated normal case, and correlated non-normal case. So this one should be the last one. So based on this, we will make our function file to so that that can handle other also other kind of variable also. So how we have solved that uncorrelated normal case? We have solved different kind of problems, but let's quickly go through that simple cantilever problem where your gx was x1 x2 minus x3l. So first, these are you know random variable, so we need to convert them into standard normal space. So this is your gx in the standard in actual domain. Now we need to convert it into standard normal space. That means we need to subtract the value of x1 you know uh, with respect to Z1, Z2 and Z3. So we will get that GZ in standard normal space. Now, once we have that GZ in standard normal space, now also we have one more relation like Z equals to alpha into beta. So Z1 equals to alpha 1 into beta, Z2 and Z3 will go like this. So if we put all these things in this equation, so we will get that uh, limit state function in the standard normal space. Now once we have that limit state function in the standard normal space, now what we need to do, we need to find out the derivatives of the limit state function in the standard normal space so that we can find out the direction cosines. So once we have that derivatives, so we need to start our iteration from initial betas and initial alpha. So once we have that initial values, you can directly put them or use them to find out the alpha values. So once we get that alpha value, based on this alpha value, we need to solve that equation, right? That gz in the standard normal space. Like if we put all the values here, what is that? Alpha 1, z1, alpha 2, z2, everything is there. Now instead of z, you can write alpha 1 and beta, alpha and beta term. So you will get a quadratic equation. You need to find out the root of this equation, so you will get the beta corresponding to that alphas. Now once you get that beta, you need to find out again the direction cosines, and this iteration will continue until you get some convergence or until you get that your stopping criteria. So here we have seen that if we put some stopping criteria tolerance as 0.001, so after third iteration we will get the convergence and we will get the beta as 2.2577, right? and corresponding that beta we will find the z values, because once we have found the beta we can identify that what are the direction cosines related to that beta, and once we have that direction cosines and beta, we can find out the design points on the standard normal domain, like z1 is equals to nothing but alpha 1 into beta, z2 equals to alpha 2 into beta, and z3 equals to alpha 3 into beta, so on. So once we get that z1, z2, z3, now we can easily convert it back into x domain. So these are our final design points. So that's how the Rackwitz algorithm solved the first order reliability problem, or more specifically, for the case of uncorrelated and normal case, where our limit state function will contain only the normal random variable and no correlation was there. So once we have beta, we can easily find out what should be the probability of failure, and once we have the probability of failure, we can find out the reliability also, because reliability is nothing but 1 minus probability of failure. So by this way we can see that using that Rackwitz algorithm we can easily calculate that beta. And also we have seen that lack of inference problem was also been addressed in that Hasofer-Lin reliability uh, method, has a Hasofer-Lin reliability index, concept of Hasofer-Lin reliability index. So we solved that problem also. Today we will also solve this problem using MATLAB and see whether we are getting the same results or not. And we have seen that we already, if we change the limit state from c minus d to 1 minus c minus d, we are getting the same value of reliability index and corresponding same probability of failure. That means the lack of inference problem was addressed. Okay. So this is the procedure for, this is the procedure solving that first order reliability method using Rackwitz algorithm. Now here what we are seeing, that how that Rackwitz algorithm used to solve this problem. Like we need to solve the algebraic, or we need to go for the algebraic solution of beta to find the roots of beta. Then so when we get beta, we need to find out alpha and again find out the beta. The iteration will goes like this. Now can be any other approaches so that we can find the roots numerically. So yes, there is a method called, if you use that Newton-Raphson technique, so you can easily find it out the roots using numerical solution. So Newton-Raphson technique, we all know that Newton-Raphson technique, how to find out the roots. Here we start from an initial guess and we go on up to the iteration until the convergence will achieve, and this is based on the Taylor series expansion. Now how we can use this for our problem? So here directly, if we start from some initial guess of the design points, so let's say we have that zk plus 1, these are the solution of the one kind of solution or one set of solution of the kth step. So once we have that, so we can easily expand that using the Taylor series expansion, and nothing but that initial value or the previous value plus the gradient of this. Now once we have this, and if this is a solution of this problem, so obviously this will equal to 0. That means we will get this part equals to 0. Now once we get this, we can easily simplify this equation like zk plus 1 is equals to nothing but 1 by gradient of that zk, the square, and the remaining part. So here what we are doing, we are starting from an initial guess of the root, then we will go up to the iteration until the convergence will achieve. Now here the convergence we can ensure using that two successive iteration between that points in z domain, and we will find the beta subsequently. So here what is happening, so we are bypassing the algebraic solution, and directly we are getting the numerical solution. So this is the equation for the Rackwitz-Fiessler algorithm. Okay, and here the beta is found out by norm of that final solution. So we will make a function file for this also. Once we will see all the 4 possible cases of the Rackwitz algorithm, and then we will come back to it and make one generic function file using this, and we will see or compare the results getting from both the methods like Rackwitz and Rackwitz-Fiessler algorithm. So Rackwitz algorithm generally solve beta using the algebraic solution of beta. Here we are using Newton-Raphson technique to get the roots using some numerical solutions. Okay, so let's quickly you know that visit the other cases of the limit state where the random variable can be non-normal and correlated. Once we get the clear picture of this, that how like one correlated and non-normal problem can be solved, then we can easily go to that function file and make a generic function file, like how this will go like this and what should be the algorithm associated with it. So first case, we have seen that in our gx all the random variables were normal and uncorrelated. Now if that, say maybe in that limit state function g of x equals to x1 x2 minus x3l, so for example one of the random variable are log normal, say this one is log normal. So how we can deal with that problem, or how that Rackwitz algorithm will deal with that problem, we will see. So first, that non-normal random variables, that means the basic concept is you need to look into your limit state function. Your limit state function may contain the random variables which are all normal and uncorrelated. Might be some of them might be normal, some of them might be non-normal, like log normal, uniform, type 1 largest, other type of. So first, what you need to do if we have this kind of problem, like we have non-normal variable, so first we need to convert that non-normal variable to equivalent normal variable, equivalent normal. Now how that equivalent normalization is done, I will just quickly go through it. So first, what we need to do, if we have like any arbitrary distribution or any distribution whose PDF and CTF, if we know, because if we know that this is a log normal random variable, so we and the parameters of the log normal distribution are given, so we can easily find out what should be the PDF or CDF of the log normal distribution, right? Now what we need to do for the equivalent normalization, we need to find out some reference point. Based on that reference point, we will fit the equivalent normal distribution. Okay, so first, if we have any kind of arbitrary distribution, so first select one point, that based on that point, what you need to do, you need to find out the PDF and CDF with respect to equivalent normal distribution. Now once we get that PDF and CDF, if we simplify it, we will get the equivalent normal parameter for the distribution. That means equivalent normal, we have only two parameters, mu and sigma. So mu and sigma we will get. So the concept here is like we need to first select one point, and on that reference point we need to fit the equivalent normal distribution. That means the main aim is equate the PDF and CDF of that reference point. Okay, so here, say here we have one distribution, we have select one reference point, so what we do, we find out the PDF and CDF of this distribution. That means we need to find out the area up to that point, and then once we have that two values, we can easily find it out the parameters. Now once we have the parameters sigma equivalent and mu equivalent, and with that two parameter, if we plot the distribution, we will find this will our equivalent normal distribution. So basically equivalent normalization deals with finding out the equivalent normal parameters based on that provided distribution or unknown distribution, or that you know arbitrary distribution what is given. So if you go through that Ranganathan book or any other standard book, you will find that normal or equivalent normal parameters for different kind of distribution. So we need that equivalent normal parameters to make a generic code. Like if we have log normal distribution, if we have uniform distribution, if we have type 1 distribution, how to convert them into equivalent normal distribution. So here the concept, just I went through the concept, like you just need a reference point, and on that reference point you need to fit the equivalent normal distribution, and you need to find out the parameters of the equivalent mean and equivalent standard normal equivalent mean and variance of or standard deviation of the equivalent normal distributions. Like if we quickly go through some example of it, like if we have a normal distribution, okay, here if we have a long normal distribution whose PDF is given, and we need to find out the equivalent normal distribution with some reference point 1.5. Now the reference point is important. If we change the reference point, then equivalent the parameter for the equivalent distribution or equivalent normal distribution will subsequently change. So here what we need to do for log normal distribution, we know the PDF. These are the two parameters of the log normal distribution. Once we have this, we also seen that how we can calculate the PDF and CDF for the log normal distribution using standard normal variate. Now once we have all this information, we can easily find it out the equivalent, sigma equivalent and mu equivalent. Now for log normal distribution, the sigma equivalent is equals to x star sigma ln x. Now x star is nothing but your that reference point based on which you are doing the normalization or equivalent normalization and mu. Now once we have these two values, we can easily calculate what should be the equivalent normal distribution, or what, so how that equivalent normal distribution will look like. So here we can see that once we have these two values and we put the values to get the numerical digit, or to get the values, final values, so we have seen that the for the log normal distribution, the sigma ln x and x bar was that, and for the equivalent normalization we will get these two values. Like if we plot the log normal distribution based on these two values, we will get this curve, and based on these two values we will get this curve. This is nothing but your equivalent normal for this normal distribution table. So here the logic is like the area under these two plot with that reference point, we are making them same. So if we have this kind of problem where we first need to you know uh, convert that non-normal to normal distribution or equivalent normal distribution, so how the Rackwitz algorithm goes in this case. So first, all of the steps will be same. Like we need to transform the gx into z space, we need to find out the derivatives with respect to z1 z2 z3, start with initial guess, and now here we need to find out the equivalent normal parameters like equivalent mean, equivalent sigma. If two parameters are there, if one parameters are there, then we need to find out one parameters, and then rest of the algorithm will goes like same. Okay, so if we quickly go through one problem, like here previously we have solved that all three random variables were normal. Now here what we have done, that instead of normal random variable we put that okay, x2 will follow log normal distribution. So what will be the change here? Like here instead of x2 we need to, like here x1, what we are doing here, directly convert into z space, but here what we need to find it out, equivalent normal mean and equivalent normal sigma for this case, and then we can proceed the iteration of the solution. Okay, so we will see this step by step of why once we reach that final case where that correlated and non-normal random variables are there, and we make some function file, then we will solve this all problems, and we will see how that results will vary, or if there is any variation of results, or anything we will check later. Okay, so basically you need to put additional step where you need to first you know convert it into equivalent normal space, and then rest of the operations are same. So here we can see that after third iteration we will get the convergence and we will get the beta also. Now we will see that now the fourth case, that most generic case, that if we have you know correlated, this one is the third case, correlated and normal case. So if we have correlated random variables, that means, say let's say x1 and x2 are normal, but they are correlated with some correlation coefficient, say 0.5. So what will you do? That means your gx is correlated now. So you need to first uncorrelate them. So say for example, x1 and x2, they are correlated. So how this correlation can be defined? So that correlation can be expressed or defined using the covariance matrix or correlation of coefficient. So let's stick to covariance matrix, that that uh, that the correlation is expressed using that covariance matrix. So first, what we need to do, we need to uncorrelate that random variable. That means we need some orthogonal transformation. So if we have a random variable x1, x2, x3, and they are correlated, and the correlation is expressed by like covariance matrix. So the covariance matrix will look like that, like your diagonal term is the variance and the off diagonal term will deal with the correlation. So to uncouple this, we need to have a transformation, and that is x is equals to v into y. That means we are transforming the random variable x to y using some transformation matrix here v. Now, what is that V? V is nothing but the eigenvector of Cx. Eigenvectors of Cx. Okay. So if we perform the eigenanalysis on Cx, we can easily find out the eigenvectors and eigenvalues of Cx, right? Okay. So that means our X space is the correlated space, Y space is the uncorrelated space. So in Y space, what should be the parameters of the random variable? So we can easily find it out using basic statistics, like E of Y will be nothing but V transpose E of X. You need to remember these formulas, because when we going to write the code, this will be useful. Like what should be the mean of the uncorrelated random variables, because X domain is correlated domain, Y domain is the uncorrelated domain. So here we can easily find it out, like some properties, orthogonality properties, and all these things we can find it out. And we can easily find it out what should be the variance uh, of that uncorrelated random variable in y domain. So it will be nothing but the eigen values. So lambda, we can easily find it out. So Cx will be nothing but your eigen values of the Cx matrix. That means that uncorrelated covariance matrix will be nothing but your lambda of, that means what is the lambda? Eigenvalues of that Cx matrix. Okay. So in uncorrelated domain, my mean of y is nothing but v transpose into ex. What is that v? V is nothing but the eigenvalues of the Cx. That means correlated random variables, the variance of the correlated random variables. And cy, that means uncorrelated, that your covariance matrix will be nothing but your eigen values. Okay. So let's quickly solve one example so that this concept will get more clear. Like if we have two random variable with correlation coefficient 0.35, now uncorrelate them. How we can uncorrelate them? First, we have that, okay, we have two random variable x1 and x2. The mean of x1 is 34, sigma of x1 is 3.4, mean of x2 is 50, and sigma of x2 is 10. And the correlation coefficient is also given, like rho is nothing but your 0.35. So what should be the Cx matrix? That means correlated covariance matrix. So that will be sigma x1 square, here sigma x2 square, and rho into sigma x1, sigma x2, again rho sigma x1, sigma x2. So you will get 2 by 2 matrix, and if you put all these values, you will get this matrix. This is your correlated random variables, the covariance of the correlated random variables. Now how we can uncorrelate them? You just need to have that transformation, like x is equals to v into y. So first, we already have seen that transformation, and we have already seen that what should be the mean of that uncorrelated random variables in y space. So mean mu of y will be nothing but your V transpose into mean of X. So mean of X, here we know 34 into 50. V, what is V? The eigenvalues. We can easily calculate the eigenvalues and eigenvectors from the characteristic equation, or using MATLAB EIG command. Easily you can find it out, the eigenvalues and eigenvectors. So once we have performed this eigenanalysis and found that what should be the eigenvalues and eigenvectors, then we can easily find it out the mean and covariance of the uncorrelated random variable, or we can say in uncorrelated space. So here we can see that in X domain they are correlated and there some correlation coefficient was there, but once we transform them into uncorrelated domain through that X is equals to V into Y, that orthogonal transformation, we have seen that the correlation is not there, but we have same points, same number of points uh, as x1 and y1, same number of points should be there, but what happened, like the correlation, or we just uncorrelate the the correlated form. Okay, that means the uncorrelated, that uncoupling thing is done, or the decoupling thing, sorry, not uncoupling, it's decoupling thing is done here. So first, what we need to do if we have this kind of problem and we need to solve it. So first, here additional one step will be added to the Rackwitz algorithm. Like first, what we generally did, if that correlation is not there, directly we convert that X into Z domain. Now what we need to do, first we need to write that gx is equals to 0, then we need to convert it into y domain, that means gy is equals to 0. That what is that y domain? It is the uncorrelated space, right? Now once we have that uncorrelated random variables and the parameters, we can now convert it into Z domain, right? So intermediate step we need to perform, and finally the transformation, how the transformation will look like, that X will be nothing but V into mu y plus V into sigma y into Z. Recall like how we have transformed it. Z equals to, first, if that was uncorrelated case, so Z1 is equals to x1 minus mu x1 by sigma x1. If it is uncorrelated, now correlation is there, so first we need to convert it into gy, then gz. So from y to z, here yi minus mu yi by sigma yi, and we have the parameters of y space like mu y and sigma y, and if you put this you will get this expression. So this is also a very important expression, like when you have that correlated random variable, so first you need to uncorrelate them and then you need to convert that into z space. Okay, so how that algorithm will look like, this will be the final version, like here not final version, here the correlated case only there, and correlated plus non-normal, that will be our final target to make that function file. So let's see how we can solve using that algorithm. First, what we need to do, we need to find out the eigenvalues and eigenvectors of your Cx, what is given. Then we need to make the transformation like x to y. Once the transformation from x to y is done, we need to convert it into y to z, right? So directly here, if you want to write it down from x to z, we can write x is equals to v into mu x plus v into sigma y, mu y, and v into sigma y into z. Directly we can write it down, or I can put some intermediate step and we can write write that that intermediate step in between that two, or we can directly found it out like x to z, right? Now once we have all the random normal random variables in the standard normal space and we have the limit state function, the rest of the procedure will be same. That means we need to find out the gradient of the limit state function in the standard normal space. We need to assume some initial value of beta and alpha. Based on that beta and alpha, we need to construct that algebraic equation to solve the beta. Once we have the beta based on the initial alpha and alpha values, so again we need to find out the new direction cosines, and from this step to this step it will continue until the convergence will achieve. Okay, now the most last case where correlation and non-normal will be there. That means your random variable will be correlated and maybe some non-normal random variable will be there. So how we need to deal with that? So just go through that algorithm and we will go to make a function file of it. So this is the final version. Like if we make a function file of this that can handle all above other things, like how I will tell you. So first, how we can solve the problem where correlation and non-normal variables are there. First, what we need to do? First, we need to perform the eigen analysis of your given Cx, right? It will check either the Cx is correlated or uncorrelated. If correlated, it will perform the eigen analysis. Now, once the eigen analysis is done, that means we have V and lambda value. Once we have V and lambda value, that means we will get the parameter of y space, that means mu y and sigma y. Once we have that two parameters, we can directly convert that x into z. That means here the intermediate step I have omitted, directly x to z I have written. Like you can easily write it down, v into mu x, v into sigma x into z, right? Now once we have all the parameters in standard normal space, then we need to evaluate the gradients of that Lemstedt function to get the direction cosines. So first, what we need to do? First, we assume some values of beta and alphas. Based on that betas and alphas, first, what we need to find out, that is there any kind of non-normal variables are there. If any kind of non-normal parameters are there, we need to first convert it into equivalent normal parameters. Now, once that equivalent normal parameters, the conversion is done, we can express the limit state in terms of beta and alpha. Now, put the initial beta and alpha, we can solve for first beta. Now, once we get the first beta, we again put the values and get the direction cosines again. Then again using that direction cosines, get the new beta, and the iteration will continue until we will get the convergence. Now the convergence achieved, like we will get some tolerance, say beta k minus 1 minus beta k, or beta say k to k minus 1. If the tolerance is something say 0.001, whatever you want to put the tolerance for your problem, then that algorithm will stop there. And once we have beta and alphas, we can easily calculate the z1, z2 and z3s. And once we have z1, z2, z3, we just convert it back to x1, x2 and x3, and that will be our final design points for solving the problem, of solving the reliability problem. So today what we will do, today we will make the function file for this algorithm, right? Where all the cases are there, like non-normal, correlated, all these things, and we will make it in a way such that that function file can handle all other problems. You just need to switch the variables, or you need to put some additional steps to get that. So our first goal is to make a function file of the Rackwitz algorithm which can handle all kind of problems. Like we have four kind of problems. One is uncorrelated normal, then uncorrelated non-normal, then correlated normal and correlated non-normal. So four cases. So based on this flow, or based on this logic, we just will go to make that function file, and we will see, or we will solve different kind of problems. So basically today we will do that Rackwitz and Rackwitz-Fiessler algorithm both at a time, and we will solve the problems. Okay, so first let's go to that MATLAB and let's make that function file and solve some problems. Then we will come back and we will solve that problems in pen and paper for your assignment purpose. Okay. So till now, do you have any queries or you need to ask something? Ask me. Then we will go to that function file.
No, it's perfect.
Okay. So just previous day I have shown that function file, but that was like based on this last version. So I think that some steps were unclear, like how these steps are coming, how we can incorporate this within that step. These all things, all confusion were there. So today that thing will get clear. So we will make two function file of first Rackwitz algorithm and the Rackwitz-Fiessler algorithm. So let's go to quickly go to the MATLAB editor. So, Bob, have you installed MATLAB?
I tried, but had some difficulty. So
Okay,
hope to enjoy it.
okay. So today, actually, we will go to step by step so that the function file which I provide, you can use it or utilize it or modify it for your own purposes. Okay.
Okay, thank you.
But you need to install and practice. Otherwise, these things will not, get clear.
Tell you, I'm only watching. I don't have better understanding of the whole thing, but
Okay, no, we will
hope to
solve
be
that
able
problem
to. Yeah,
using pen and paper. We will solve that problems using pen and paper so that that will be helpful for your assignment purpose. Okay, so
thank you.
okay, is my screen visible? Yeah.
Yes,
Okay. So our goal is to code this or to make a function file of the this Rackwitz algorithm, right? So first, what we need to do, we need to like check whether our random variables are correlated or not. So like here, this is the function file for Rackwitz algorithm. So how this function file goes? So here I name it like form new. You can name it differently like Rackwitz algorithm or any kind of name you can put it here. But this name should be consistent while you are calling that function. Okay. So here what I have done, like I am making this function file using the input, like I will provide the question number. From the question number I will get the limit state function and I will supply the input variables. What is that? X is the random variables which or the number of random variables which you have in your limit state function. That mu x, these are the means of your random variable in actual space. Cx, this is the covariance matrix. Bx, that is the initial guess of beta. Now index, I have provided index. That means using that indexes, I will differentiate between the random variables. Like if I have normal random variable, I provide the index 1. If I have uniform random variable, I provide the index 2. I will tell you when that index will work. And then I have provided one switch. This you can provide it or also you cannot. Like I have use one switch where you can solve the roots using the Newton-Raphson technique. You know, instead of root findings technique. This means this is not like that Rackwitz-Fiessler algorithm. It's Rackwitz algorithm only. Like solve-winner. For now, this input you just forget it about that solve-winner. I will be back into it later. First, let's see the Rackwitz algorithm as it is. Okay, so this is my input. Now I need to define that what should be the length of my random variable, number of iteration need to perform, and tolerance. I have provided the tolerance is 0.001. So here you can control like number of iterations, how much iteration you need to make, and how much tolerance you need to provide to stop the iterations. Now to load that random variable in symbolic form, so I use that symbolic form of b, and you that load that random variables in this form. Now first, what we need to do, if you go back to your uh, algorithm, so you will see first we need to find out the eigenvalues of the problem. Now what I said, in your problem the random variable can be correlated, can be uncorrelated. So first you need to make one logic, so that what it will first check. That means you are providing the cx, providing input cx. Now it will check that your cx, that means the covariance matrix, is diagonal or not. Diagonal, if diagonal, that means Abdul, if your cx matrix is diagonal, that means
It is not correlated to others.
yeah, it is not correlated. Now if it is not correlated, then it will directly take d as cx. D, what is that? D, that means your eigen values, directly it will take d. That means it will not perform the eigenanalysis. Now if not, then it will perform the eigenanalysis of cx. So eig command is here, is used for find out the eigenvalues and eigenvectors. So v is nothing but the eigenvector and d is the corresponding eigenvalues. So in that portion, what that function file will do, it will check your input covariance matrix, that is it correlated, that means is it a diagonal. So if diagonal, then we don't need to perform the eigenanalysis. If not, then do the eigenanalysis. Great. Okay, now once the eigenanalysis is done, what we need to do, we need to write the parameters in y space, right? So y space, what was that y space? Mu y. Just sometimes back we have seen that mu y is nothing but v transpose into mu x. Yes or no? We have just seen it. Mu y is equals to v
Yes.
transpose into mu x. This one, right? And cy is nothing but v transpose cx into v, and that is nothing but your lambda matrix. That means your eigenvalues matrix. Now here that thing have done. Now sigma y I have put. Now that this is the initial alphas for the iterations. Now once I have that, I can easily write that my z1 is equals to beta into alpha, that initial alpha, and I need to make the transformation from y to z domain, right? So from y to z domain, we are here coming from x. Y is the uncorrelated space, y we have here. Now we need to go to z. So what was the transformation? Last transformation from x to directly z, v into mu y plus v into sigma y into z. That is nothing but is equals to x. So look, precisely that I have done here. X1 is equals to v into sigma y multiplied by z1. That means the last part I have written here, initially, and v into mu y. Nothing but your that transformation, right? So now what you need to do? Just let me go to the layer. So first, what we have done? We are find out that eigen analysis, and then we transform it into that. Now think think if we have one case where correlation is not there, so what that code will do, that will directly pass that cy, that means here that x1 is directly converted to z1, that means x1 will be equals to mu into that sigma into z1 plus mu x1, that formula simply. Okay, now what I need to do, or what that code need to do, that first you need to check you have converted into z domain. Now what you need to do, you have converted, once you have converted into z domain, now you need to first find out that is there any kind of equivalent normal parameters or not. First, our initial alpha and betas we are already providing it, so first we need to find out is there any equivalent any non-normal parameter whom we need to convert it into equivalent normal. So here look, the equivalent normalization is done, like mu equivalent and sigma equivalent, it will check either it is like index. Initially I have told you like that index I am used for the for identifying the random variable. Like here I am giving that mu x and sigma x, and I am calling one function file which I name it equinorm. Now what equinorm does, like that equinorm function file is doing the equivalent normalization based on parameter x, that means random variable mu, like what was the parameter for that random variable, and sigma and id here look, id will define like for this case id1 is equals to normal distribution, id2 uniform distribution, id3 you know log normal, and id4 for external distribution for type 1 external distribution, or type 1 largest distribution, or we can say Gumbel distribution. So for this four distribution I have made the equivalent normalization function file. So if you provide x, mu, sigma and id, it will give you the equivalent mu and equivalent sigma. If both are normal, then the id will be 1, that means mu equivalent is equals to mu actual and sigma equivalent is equals to sigma actual. Clear? So in this domain, or in this region, what we are doing, we are checking is there any non-normal random variable are there or not. So this code can handle like four kind of random variable. One is normal, because I have put four type of conversion of equivalent normal distribution, but you can you can add more of them. You will find in a standard book like what should be the parameter of the, like you can easily see for log normal distribution we have seen that sigma equivalent and mu equivalent formula. We just have seen on that example mu equivalent and sigma equivalent. So for id3, that means if you have log normal distribution and you need to convert it into equivalent normal, so you need to put that id3, you need to put that random variable, that mu of that random variable and sigma of that random variable. This function will give you the mu equivalent and sigma equivalent, right? Now once this is done, so we can convert it into z domain whole thing. So that this is nothing but mu v into mu equivalent plus v into sigma equivalent into z, like this one, this this equation, right? So once we have all this in z domain, like here I have written the expression here. Now I am calling a function which contain my limit state. Look, until now uh, we didn't pass any limit state function based on the random variable, so it have to have the limit state function. So here the gsc function will give me the desired limit state. Like if I put the question number and random variable, it will give me the random variable. Now I made this function file separately so that I can handle so many problems at a time. You can make it another way, like here itself you can add the limit state function so that you can call it, but it will not be generic. Like what I need some code. Just you put the inputs, it will give me, or you put the input and that limit state function, it will give me the desirable value of probability of failure, then the design points and the reliability index. Okay, so here the ones we have converted into Z space, like here I am calling that my limit state using Qn and Gz. So in that line, actually my, you know, Gx is converted into Gz. Okay, now once we have that Gz, what we need to do? We need to find out the derivatives of the limit state function in the standard normal domain. Like here, look, the derivatives are dgj first differentiation and dgz, we will get that values of this differentiation. Now look here, I'm using that vpa command, value precision point command. Like when you are using that symbolic variable terms, so you need to, when you need to, when you know decide to get the values in numerical forms, you need to have that value precision point command. Otherwise, that you will get different kind of values, you might get different kind of values based on not that precision point. So if you use that vpa command, it will get, when you convert to symbolic to numerical values, it will get the exact values. Okay, now once the differentiation is done, that means now I can get the direction cosines. So alpha is nothing but, recall, alpha is nothing but norm of or that gradient of uh, that um, gz or limit state function in standard normal space with respect to the random variables divided by norm of your limit state function. Like we have already calculated these things, uh, where that thing is, like alpha I is equals to nothing but uh, norm of this Euclidean norm. Like first thing we will get that very beginning. Yeah, like alphas are nothing but the gradient of the that limit state function with respect to the random variable divided by the Euclidean norm of the limit state function as a whole. So now we have the direction cosines. And once we have the direction cosines, we can start the iterations. Like, yeah, okay. So z is equals to nothing but alpha into beta, and we substitute these all values into gz, like this equation. In this equation, substitute all these values in this equation. Now here in this line, when we substitute that z value and beta value, or z value is calculated using that beta value, so we will get here within that line we will get that algebraic equation of beta, right? Now what we need to do, once we get the algebraic equation of beta, we need to solve for beta. So here root, we need to find out the roots of beta. So either you can solve using b root command or solve command, or you can use other function file like Newton Raphson technique I have used to solve it. But I will suggest that b root command will itself sufficient to solve that roots, or else you can find out different type of root finding algorithms if you have. Now once we have these two values, then it will start iterating, and it will go until the difference between that two consecutive beta, bx and b2, if it is within that tolerance limit, then the loop will break. Otherwise it will continue until the tolerance will achieve. Now once we have the final value, what it will give, it will give that final beta, final alpha, final z value. Now once we have final beta, final alpha, we can convert them into x domain. So these are your final design points on the x domain. So it's nothing but the inverse conversion, like v into sigma equivalent plus z multiplied by z plus v into mu equivalent. Like once we have converted from x to z, here we can convert back to z to x, like the reverse conversion. Now it will print your beta, your z value, and it will give that probability of failure. So this how this function file will work. So what we have seen, to call this function file, what we need to provide the question number. From the question number, what we are getting here, the limit state function, right? The limit state function. Now we need to provide x, that means the number of random variables, mu x, the covariance, beta x, that means the initial values, index for tackling the equivalent normal or non-normal problems, and here you can give that Swiss or not in your as per your convenience. You can give it, or you can you can bypass it. Okay, so this is the function file. If you put this inputs, it will give you the beta value, probability of failure value, and final design points, right? So to call, this is the function file. To call it, we need a script. Like, let's say we will solve one problem. Let's solve one problem so that this will get clear. Then we will go to Rackwitz-Fiessler algorithm. Say for example, let's solve one problem so that this thing will get more clear. Okay, let's say we will solve a known problem. Okay, let's solve this problem. Okay, cantilever beam problem. So here what that problem says, that we have a limit state g of x is equals to x1 x2 minus x3 l. Clear? Okay, so first let define our limit state. So here I have defined that limit state in another function. I already have explained. Like here, look, for if the question number is 1, then this function will give me or allow me to access this limit state. So x1 x2 minus x3 into l, I think l was 2 meter, l was 2 meter. That's why I put that 2 into x3. Clear? So this is my limit state function. Now what I need to do, I need to provide the parameters for the random variables. Now I need to provide it. So here, this is the main script from where I am calling that function file, right? So first, let's say I need to provide the question number. Why I need to provide the question number? Because based on the question number, it will pull out the limit state function. Now I need to um, provide the cx. So here, look, what was the cx matrix for this cx? Tell me, what will be the cx matrix for this case? What will be? Is there any correlation? No. So Bob, what will be the cx for this? Nothing but your sigma x1 square, sigma x2 square, sigma x3 square. Yes or no? Abdul? Yes?
Yeah.
Yeah.
Yes.
So we can have these sigma values. So easily we can make the covariance matrix. So let's make it. So we have 2.5 into 10 to the power 4, 6 into 10 to the power 4, and 15, these values. So here I have put all these values in a matrix form. So first, this sigma of x1 square, sigma of x2 square, sigma of x3 square. Clear? Now I need to put the mu values. So already we have the mu value, mean of x1, mean of x2, mean of x3. So let's quickly put the mean value. So mean of x1 2.5 into 10 to the power 5, 1.2 into 10 to the power 3 minus 3, and 100. Correct? Now what we need, recall, to call this function file, we need, so here I have provided question number, I have provided mu, I have provided cx. I haven't provided the number of random variables and initial beta and index x. So let's do it. So first, initial beta, let's say 3. Now index, look, here all the random variables are normal, 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 normal. That means if we go to that equinorm function file, we can say that for normal random variable we have index 1. That means we don't need to perform the equivalent normalization things here. Okay, so what will be the index for three random variables? 1 1 1. Okay, now how many random variables are there? Three random variables are there, so I need to put that 1 2 3, three random variables are there. Now I am in a position, okay, I have put all these values. Now I can call my form new function file. So for now, form m2, just close it. Clear? Can I call it? Yes, because I have provided all the values qn, I have provided x, I have provided mu x, cx, beta x, index, and this you can off, or you can, like here, look, solve winner false. False mean it will solve, or it will find the root of beta, or it will solve the algebraic equation of beta using broot command. Broot is a inbuilt function file, inbuilt command of MATLAB. You can easily find it out. Or if I put that yes for this switch, then it will find out using Newton-Raphson root finding technique. So here, actually, here why I am saying that this switch is not useful, because we will make the Rackwitz-Fiessler algorithm separately using that matrix equation we have already seen. That will be more handy to operate and more computationally efficient, rather than using that Newton-Raphson command using here within the Rackwitz algorithm. Okay, so stick to that broot command. Now if I call this function file, what it will do? Let's call it. Okay, it start iterating. So what it will do first, when I will provide these values, it will call this function file. That means first it will check whether that cx is diagonal, or is there any off diagonal term is there. So is any off diagonal term is not there, because for this case there was no off diagonal term, so it will directly bypass, and it will take cy is equals to directly d. That means d is equals to nothing but cx, whatever I have provided. Now it will check whether the equivalent normalization may be or can be done, or might be, or need to be done or not, so here that index says I have provided 1 1 1. That means all are normal random variable, so the equivalent normalization thing will not do. Okay, now once these things will done, then it will transform the limit state function into z domain. So how? Here gz equals to nothing but you provide the question number from where it gets the limit state function in actual space, and xz value, like xz, these are the this is your transformation function, like xz equals to nothing but v, like xz equals to this part should be in front. So in MATLAB you can either way you can put it that. So v into mu equivalent plus v into sigma equivalent into z. We have seen this. Okay, so now check whether our beta and final beta. So after getting all these things, what it has provided me, it provide me that after third iteration I am getting the beta as 2.5 2.2576, and these are the design points in z domain. And once we get these two along with our direction cosines, I need to find out the xf values and the probability of failure value, right? So by this way I can easily calculate the this function file will give me the final beta, final design point in z domain, final design points in x domain, and corresponding probability of failure. Now for example, say say in a problem. So here how much beta we have found out? 2.2576, and already we have calculated this, and we seen that the final value of beta after third iteration we are getting it like, yeah, 2.2577. So 2 point, here we are getting 2.2576, like that much of error. Like here I have taken up to 5 digits, maybe that was taken up to 4 digits. So this much of error, that 0.000, that is absolutely okay. Okay, now For example, let's say one of the random variables are log normal. So for example, we have one of the random variable that is log normal. So let's say we have another problem where log normal. Say for example, second variable is log normal. So what we need to do here? What we need to do here, Abdul? Just change the index for the second variable. So log normal case, I think 3 was the log normal case, right? Equinorm, if you go, yeah, 3 is the log normal case. So here, what I have changed for this index, like, okay, my second random variable is log normal. Okay, now run it. Now, obviously, look, the beta fn has changed 2.2537 and pf is changed. And the values, whatever we have getting from here, are the same values whatever we have calculated earlier, 2.2537. Clear? So that means using that function file we can easily handle all of the problem using some switches, because we have different kind of functions for to handle different kind of problems. So and it is checking step by step whether that four conditions, out of that four conditions, which conditions I need to, or that code need to satisfy, and so on. So this is actually, we can say, okay, this is the function file of the Rackwitz algorithm, which can handle other kind of problems, like for example, like let's solve another problem where you know where we will see different kind of random variables. Like I have added here the few problems which we will going to solve using Rackwitz-Fiessler algorithm. So that was the Rackwitz algorithm as a whole, and this function file will serve for Rackwitz algorithm. So let make the function file for Rackwitz-Fiessler algorithm, and we will check the values simultaneously. We are getting the same values using Rackwitz and Rackwitz-Fiessler algorithm or not. So if you have this function file, you can solve the Rackwitz or the up to the correlated non-normal problem using, that means all kind of problems using Rackwitz algorithm. So I hope this function file and the logic of these function files, or logic of the codes whichever I have uploaded on the previous class, is clear now. Is it? Is there any doubt, Abdul?
No.
Okay, so let's quickly go to that Rackwitz-Fiessler algorithm. Okay, and make the code for it. So what was the logic of it? That we are numerically, here we are we need to solve that beta algebraically, and there for the Rackwitz-Fiessler algorithm we just, or we will solve that uh, that using numerical techniques. So finally this form of equation, matrix form of equation, we need to solve it, or we need to put it in our function file. So let's say, let's make a code for this. So form m2, I name it like form method 2. You can name it like form Rackwitz algorithm, a Rackwitz-Fiessler algorithm, RF algorithm, whatever you want to do. But while calling it, you need to enter the exact same name, otherwise it will not call. So here what that function file will what that need, like you need to provide the question number, x, mux, cx, beta, and index. Okay, and it will give the beta and final pf. Here you can add your like x values, in final x values, z values, and all these things. You can you can modify this as per your convenience to get different kind of values. So first, this code will also, the flow of this algorithm will also same, like it will first check your covariance matrix, because you are giving the input of the covariance matrix. So it will first check whether your covariance matrix is correlated or not. If it is correlated, then it will perform the eigenanalysis, and it will set the parameters for the uncorrelated space. Now once this uncorrelation is done, obviously it will look for the equivalent normalization. If they are equivalent, it will do the equivalent normalization, and subsequently it will give that it will get the equivalent normal parameters, equivalent sigma and equivalent mu. Now once we get that, we convert it into z domain like here. So here up to this point we have our limit state into z domain. Now go to that technique. What we need to do first, we need to start from a solution, and then we need to look for the convergence. So basically we need to write this equation. What is that? Gradient of g z k. So once we have that g in z domain, now we can perform this matrix operations like here the initial values are given and initial tolerances are given. You can easily find it out like here. Now dgz is the gradient of z. That means the limit state function in standard normal space with respect to z. Now it will find that values of first value, that dg into xk. Then actually uh, these three equations I have separated it like this part, and for this part I have separated out like here you can see, and I have written it also here. uh, if you go like a little here, one second. Yeah, here. So for the first part, what we need 1 by gradient of g zk whole square. So this part I have write it down like this. So 1 by norm of g of xk. Now norm of g of xk I have already here find it out. Now here I have just for the simplification I write it down these terms separately. Now this is the bracket term. If you go here, this is nothing but this gradient of zk multiplied by zk minus g of zk gradient of zk. This term is absolutely written here. Look, dxk hat multiplied by x all comma k, that means that particular form it will find it out, and d of zk. Now that ESC3 to make this equation assemble like z star xk plus 1 is equals to 1 by this multiplied by this. So here this part, for this part I have like expression 1 and expression 3. Right here we will get the final expression. So ESC3 will nothing but ESC1 into ESC2. This part will get multiplied by dg into xk already we have found out. So in that line number 47, our this matrix form has been established. Yes or no? Now once we have that, we will start our iteration and look for the convergence. One, we will get that if we will get the convergence. Now we will stop there, and for this case beta will be nothing but norm of this. Now once we have found out the beta, it will display okay, that will be beta using Rackwitz-Fiessler algorithm, and it will subsequently give us the probability of failure. So probability of failure is nothing but phi of minus beta. So this is the function file for the Rackwitz-Fiessler algorithm. So now for to call this algorithm, what we need, we just need that same parameters here. What I said before, that our intention is to make one function file and one script, so that we can call all kind of problems, and we can handle all kind of problem in one script. So like here for the same problem, say for 111 case, that means all are that cantilever beam problem, if we go to that problem here, the cantilever beam problem, first we have solved it using Rackwitz algorithm. Now if we want to call it using Rackwitz-Fiessler algorithm, just look, first I am calling form new. Form new is the nothing but the Rackwitz algorithm, and form m2 just we have created that function file for Rackwitz-Fiessler algorithm, right? Now so now I can call them using this functions. So if I call it, let's check whether my two method giving me the same beta and probability of failure or not. Say, let's run it. So first it will calculate using Rackwitz algorithm. So using Rackwitz algorithm, it's find out the beta is nothing but 2.2576. Already you have seen. Now it is calculating using form M2. That means Rackwitz-Fiessler algorithm. And look, we are getting the same values of beta. Yes or no? We are getting the same values of beta. That means our function file and the logic, whatever we have coded here, is right. Okay. Now we can check another problems also. Here in this function file from M2, you can write or you can call your, or you can display your, x points, z points, and all this. You can make necessary modifications here to call to get different kind of output. So for here, for comparison purpose, I only opt for two output, beta and pf, and it is giving the beta and pf based on my initial values. So here this is the main file from where I am calling all of the function files. So here that from new will give me the results using the Rackwitz algorithm, and from M2 will give me the results using Rackwitz-Fiessler algorithm. And we are seeing that the final results of the cantilever beam problem we are getting same, like 2.2576 and 2.2576. Yes, like if you want to call only one function, what you need to do, just comment it. So now what that code will give you, only the results using the Rackwitz-Fiessler algorithm. Now it is calculating it, it will just print the result. Yeah, so this is your final beta using Rackwitz-Fiessler algorithm, and this is your probability of failure. So for this case, we are getting the same results. So there might be some different kind of difficult limit states where root finding is not that much easy. So we might get some different result using that different tool. Now your task is to solve different kind of problems. Like once we have that two function files, now we can solve a lot of problems. Just you need to provide the initial values, provide the random variables, write the limit state function properly, and you can set to go. Right, we can solve different kind of problems. Let's, here I have added 8 number of problems, you can solve it. So first problem, what we have solved, like we have considered the limit state x1 x2 minus x3 into L, right? So that should be x3. Please make it correct, x1, not x1. X2. Great. Now now if we change the limit state in that format, let's see, is there any change for our beta? Recall that while we are solving problem using mean value first order second moment method, we have seen that when we have changed the limit state, the final estimate of beta have changed, right? Now let's see, we will change the limit state to this format. Like now we have the beam or the limit state in this format. So the limit state is now gx is equals to 1 minus x3l by x1 x2, right? So I need to write it down. So let's say make it question number 2. Rest of the inputs are same, but the my limit state will change. So here make a new limit state, question number 2, 1 minus 2 into x3 divided by x1 into x2. Clear? I have written the limit state in actual space. First my limit state was x1 x2 minus x3 into L. Now I have written the limit state in that format. Now let's see I am getting the same results or not. So for the first case, what was the result? If all the random variables are normal and uncorrelated, the result was 2.2576. Clear? Now let's say we are checking the second one. So what you need to do? Here you need to just change your question number to 2. So that means it will first look at the question number and go to your limit state function. I'll check what is my limit state. Okay, this is my limit state. And all the parameters like Cx, covariance matrix, mu x, initial beta, and index. Look, we are considering all the random variables are normal for the first case, because normal to normal we are comparing. If you want to change the random variable to log normal, you just need to change the index here. So log normal index equinorm, you just need to go to equinorm, look for log normal. The index 3 represent the log normal, index 2 uniform. Now you can fill this equinorm function file with other, like here I have done up to Gumbel. You can do like type 1 largest, different kind of like if we have another set of random variables. So mostly these four random variables is sufficient to solve most of the engineering problems. So that's why I put four. Okay, now let's see. Now I am calling that. Okay, let's check this problem considering that two method. Okay, I'm calling the form and form M2. That means using Rackwitz and Rackwitz-Fiessler algorithm. So you just need to change question number. I have changed the question number. Now just run it and let's check we are getting the same value or not. Okay, so it has calculated the value for Rackwitz algorithm, and it is giving the exactly same value, 2.2576, and from method 2 it has already solved and it also gives the same value, 2.2576. So what we have seen here, that the lack of invariance problem, whatever we have encountered during the mean value first order second moment method, get resolved or get addressed during your Rackwitz or Rackwitz-Fiessler algorithm, or as a whole we can say through that Haushofer lane, the definition of the Haushofer lane reliability index. Clear? Okay. So now we have that generic function file. Now you can play with it. You just put your that limit state function properly, put the random variables here properly, you will get the result. Let's quickly solve some problems, some more problems, then we will move for that problems using pen and paper. Say for example, let's consider one random variable where correlation coefficients and all are there. Okay, let's solve this problem. Okay, calculate the reliability index 5, that problem 5 number of problem. Calculate the reliability index beta and pf for the limit state function given below. Now the limit state function is given as 3x1 minus 2x2. So first we need to put that limit state function. Say I have added its limit state in GSC function, I think here, the question number 5, right? Now you need to put all these parameters of this random variable and limit state function in that question. So question number 5 here, look for the problem statement. Here we have two random variables, x1 and x2. Then mu x, how much mu is given here? Mu 16.2 and 18.5. 16.2, so 16.5, yeah, 16.5 mu x1, 18.5 mu x2. Here I have put mu x1, mu x2, and the sigma values are also given, like sigma 1 is 2.45 and sigma 2 is 2.86, and covariance is given 2. So it's nothing but you need to make the covariance matrix. So how the covariance matrix will look like, that your diagonal term will contain 2.54 square and 2.8 square, and off diagonal term will contain 2 and 2. Yes or no? Right? Like we have Cx, we need to write it down. So what we have, sigma x1 square, sigma x2 square, and here the covariance of x1 x2, so 2 and 2. Already the covariance of x1 x2 is given, so we have prepared the covariance matrix here. Okay, now once the covariance matrix is prepared, we need to provide the index in initial value 3. Now index, look at the index here. We have, I think, yeah, one variable is normal, one is log normal. So for log normal case, what we need to do, we need to provide the index as 3. Why 3? Because in our equinorm file, we have put the index 3 for the log normal case. Now let's solve using that Rackwitz and Rackwitz-Fiessler algorithm both. Now we are ready, set to go. Now call the function. Let's see. So Rackwitz algorithm, yeah, from the, we have get the result from both the algorithm. So the Rackwitz algorithm is giving that 1.5384 and Rackwitz-Fiessler algorithm is giving us 1.54. Like 1.54 you can get the results. Like PF you can get 0.061, 0.0615. That means using that two method we are getting the same results. Okay. Now we can solve different kind of problems. Like I have added few more problems, but let's go to our that circle problem, that famous circle problem. Where is that circle problem? Yeah. Now let's solve it using, Rackwitz and Rackwitz-Fiessler algorithm. So we have that gx here in the form of this. Both are normal random variable. So just quickly put it here. GSC, what was our GSC, is nothing but x1 square plus x2 square minus 18. Now put all the variables for this case. So case 3, yeah, case 3 I have put here, case 3 for this. So go type case 3 here. Look, this is the covariance matrix, so no correlation was there. So just sigma x square and sigma y square. This is the mu, initial beta, index 1, because both are your normal variable. So now call it. Let's check whether my two algorithms, Rackwitz and Rackwitz-Fiessler, is giving me same results or not. So Rackwitz already give the result that 1.9799 and probability of failure should be 0.023. And from method M2, that means your Rackwitz-Fiessler algorithm also gave the same results, like 1.97, 1.9799, 1.9799, same results. That means now we can conclude that okay, the function files whatever we have made for Rackwitz and Rackwitz-Fiessler algorithm, these are giving me the same results, same form of results. Like we have different kind of problems here we can solve. Say for example, let's quickly solve another problem, then we will go to that problem format of pen and paper. Like say for example, this a fixed beam length 10 meter is given. Now there are two random variable like MP and WC. MP is the plastic moment carrying capacity and WC is the, that critical load. So if we have that two, and we have, that two the two parameters for these two distributions, like normal with mu that and sigma this. Now if we put this here, so first we need to make the limit state function, put the limit state function. So let's say for the last case we are going to put the limit state function here last. So what was that? WC by L, let's consider WC as x1 divided by 10. That means here if we simplify that equation, we will get that 0.8 MP by L value is 10. So 8 divided by 10, you will get 0.8, 0.8 into x1. I just simply, simplify this equation, minus x2. Okay, this is my simple limit state function. Now I need to put the parameters for the random variables. So let's say this one is our last problem, question number 8, I think. Yeah, question number 7. Okay, so in question number 7 we have defined the limit state. What was our limit state? This one, this. Okay, so once we have defined the limit state, we need to put the values. What will be the mu? 28 and 14. We have seen here that 28 is for your MP, and 14 is for WC. WC is 2, that why x2, as a x2 we have put the W2, that why 14 is later. And here the standard deviation are given, so from the standard deviation we can put the values of, or we can make the covariance matrix. And here all are normal random variable, so 1 1 is will be there. Now if we call both these functions, and we will get the value, and we will check that if we are getting the same values using that two Rackwitz and Rackwitz-Fiessler algorithm or not. So let's run it and check it. So the Rackwitz algorithm already give me result as 3.2308, and the Rackwitz-Fiessler algorithm also giving me the same beta and same probability of failure. Okay, now we can conclude that okay, our function files whatever we have made, we have tested for different kind of problems for using that two Rackwitz and Rackwitz-Fiessler algorithm, and we can now conclude that okay, we can go with that function files and solve different kind of problems. So basically what is important here, the logic of these function files, how it works, and and how to handle different problem using one algorithm, so that we can our life will be easy, nothing else. You can you can solve this problem one by one, or you can make something, so that you can call them and get the results very quickly. Okay, so here I will upload that two function files of Rackwitz as well as Rackwitz-Fiessler. Like form new, it's the Rackwitz algorithm, and form M2 is for Rackwitz-Fiessler algorithm. So I hope you understood the logic and flow of these function files, and how the first order reliability method problems, or first order reliability problems, are solved using using Haushofer-Lin reliability index, using the definition of Haushofer-Lin reliability index, and using Rackwitz as well as Rackwitz-Fiessler algorithm. The main difference is, one is numerically solve the roots using Newton-Raphson technique, and one is you know algebraic. It solves the algebraic equation of beta and then find out the alphas and all these things. Now these two methods have own limitations, own pros and cons. We cannot say that two methods are generic or other. Like in Rackwitz-Fiessler algorithm we have like convergence issue. In Rackwitz algorithm also sometimes we have some convergence issues. So then we will see we need to go for the second order method, so that these issues will get resolved. Okay, so what I will do, I will upload this function file along with the problem set whatever I have prepared, and here that problem 7 1 2 3 4 5 6 7 are as per this uh, doc file. Here that 7 problems are given, whatever we have solved using the Rackwitz and Rackwitz-Fiessler algorithm. So I will upload this as a whole. You will go through it, and I will suggest that just look into the function file, play with it, play different kind of, take different kind of GX from different books, try to solve them, or we have different kind of problems in our session already, so you can solve them, or you can check them one by one. Clear? Okay, so any doubt, or we can solve some problems using pen and paper for your assignment purpose. So Abdul, do you have any queries? Or actually you mailed me, and I was out of town, so you can directly WhatsApp me if you need anything. No problem. Okay.
Thank you.
Okay, so then let's quickly solve some problem. Okay, and please verify using calculator. Please, what is the practical application of this concept? Yeah, practical application, a hell lot of practical applications are there, man. Like if we have one limit state function, for this case, let's say for this case you have gx, you have your design points. Now you don't know what should be the optimal design points on which you should design. So you perform first order reliability method, you will find beta and corresponding probability of failure. So once you have that two, you can say these are the design points with respect to this probability of failure and this beta. That means you have some reliability with respect to this. Yes or no? Getting my point? So these are, like, we have different kind of practical applications for this. Like for this case we have seen that, one second, like simple cantilever beam problem. Let's stick to that simple cantilever beam problem here. So first, what we have seen, that in that simple cantilever beam problem, if we need to design that cantilever beam, you need that Fy, how much Fy should you consider, how much Z you should consider, how much P you should consider, you don't know. First, these all are random. And if we consider that they are normal random variable, we see that we have found one, beta and one corresponding probability of failure. Once we change the random variables, the nature of random variables, the beta and design points will change. So you need to have, you know like some method which will give you probability of failure as well as the reliability corresponding to that Z points, right? So initially these are our mean points. In the deterministic design we consider this mean point, but ultimately what we have seen, that if all follows normal distribution and uncorrelated, then finally this will be our design points. We need to design based on that, so that we can achieve beta is equals to 2.25 and probability of failure is equals to that 0.0019. Getting my point, Bob?
So this is applied after you have done your normal design because this parameters, you not get them on assuming you want to design a building, you have all your loads and using your codes, you have done your estimation, and then you've done your design to select your members. So is this thing applicable after you have finished those designs or before those designs? How will you be able to get the mean and those things if you have not gone through the deterministic figures?
like in deterministic design, okay, in deterministic design, the mean values. In deterministic design we always do the design following the mean value. Mean means, that means, like what is the E of your steel? 2 into 10 to the power 5 MPa, we all know. But this is the deterministic value without considering any randomness. Now if there is randomness in your limit state, how you can find out the final values? that was the
Mhm.
that was the first question, how we will find out that final values. So how here we have solved, how we have find out the final values corresponding to some beta and some probability of failure. So these things you need to perform before the design, okay, to
Okay,
counteract
all right.
the randomness in your limit state, the randomness in your limit state, or the randomness in your design variables, more specifically the randomness in your design variables. Okay.
Okay, all
Okay,
right.
like
Thank you.
here, P is not, let's say this P is not a point load, this P is coming from some wind load. Now that wind load will follow some distribution. We don't know if we follow that codal provision, then we can have like some factor of safety. With that factor of safety we need to do. Now if we need to make the precise estimation of this, like we are making one nuclear power plant, or we are making the reliability analysis of a important structure, then the deterministic design, okay, if I increase the factor of safety, it will counteract the uncertainty using that factor of safety. But if someone asks you for what should be the design point if I need to consider that beta and that probability of failure. Now, how can we do this? Just recall this Rackwitz algorithm. You will find it out. Getting my point?
Yes, yes. Thank you.
Okay. So it's a method using which we can say, okay, if there is randomness and your random variable are following this distribution, follow this method, you will get reliability index, corresponding probability of failure, and corresponding that design points. That means we here, like if we start designing using that three, we don't know what should be our final probability of failure. We don't know, because we don't know how much randomness is there, because to quantify the randomness we need the random variable in our limit state function, the first concept, the randomness, to incorporate the randomness. Otherwise we are happy with our deterministic designs, codal based design. That code, that like 1.53, that factor of safeties, that are also counterbalancing that uncertainties up to the certain extent. But if you need to find out you know what is the level of reliability I can consider based on this design point. So here, when I have solved this problem, now I can say, okay, if this is my case, so these are the final design points of my Z, Fy, and P. And for these design points, I can assure this much of probability of failure and this much of beta. That means 1 minus probability of failure, you will get the reliability. That much of reliability I can assure for your cantilever beam, whatever you will design using that limit state. Clear? Like that W
Yeah,
and
yeah.
cross beam
Thank you.
problem. Okay, so we have different kind of, like if you have truss, you want to design a truss, give me that limit state function, we can get the probability. Okay, if we need that probability of failure, these will be your design points. If we need to consider the probability of failure, this will be your design point. So we are getting it out of this. Okay.
All right.
Okay, is there any doubt? You can ask me. Like these all problems, these all are practical
Oh,
problems, like how we can consider it. That's all. Okay, so let's quickly
okay.
solve some
It's fine.
problems
Let's continue. Thank you.
in pen and paper. Okay, in any problem, like in soil structure interaction, in bridges, anywhere you have limit state, you have random variables, you can find out the reliability and corresponding design points. That means if you consider the design points after that calculation, you can ensure that reliability and probability of failure for this structure if the randomness is considered. That's all. Okay. So let's solve some problem on pen on paper, and please verify them. Okay. So the first problem, we have seen it using MATLAB, but still let's quickly solve it. A fixed beam L is 10 meter. Just we have solved it the problem just for this. So calculate the values of direction cosine alpha 2. The limit state is given. So how we can calculate it? First, you need to write it in X domain, convert it into Z domain, right? Now, once we have the limit state in Z domain, so this is your limit state in Z domain, GZ. After simplification, you will get this. Now, after getting it in Z domain, what we need to do? Z1 is nothing but alpha 1 into beta, Z2 is nothing but alpha 2 into beta. Put these values, you will get in terms of alpha and beta. Okay, now what do we know? Gz equals to 0. So equate it, you will get a equation terms of beta. So beta is equals to nothing but 0.84 divided by 2.24 alpha 1 minus 1.32 alpha 2. Right, now what do we need to find out? Once we have dz, we can get the derivatives of it, dg by dz1, dg by dz2. Now once we get them, we can find out the norm of that whole function, and from there we can find out the value of alpha 1 and alpha 2, 1 by k dg1 by dz1 and dg2 by dz2. So in the previous class we have solved this kind of problem, so that's why I have not dig into that. So I hope you can easily solve it. Yes, so are you getting the same results or not? Please confirm me. Okay, you just do the calculations, I will upload it, and just make sure that you are getting the same results. Okay, now let's solve the next problem, like that circle problem. We also have solved the circle problem using MATLAB. You can check using MATLAB also. So here, find out the beta in first iteration. It's a simple thing. What you need to do? First, you need to convert it into Z domain. Here, now after converting into Z domain, you need to find out the alphas, initial alphas. Once you get the initial alphas, put it into the equation of beta, you will find out the beta. First initial beta is coming out as 0.282. So have you solved, Abdul, this problem? Have you solved it? Okay, if you not, then just go through it and recheck it whether we are getting the same results or not. Now, the third problem says we are having a failure surface. Already the failure surface in Z domain is given. Now, calculate the value of reliability index for first iteration. What do you need to do? So you have in Z domain, initial values are given. Initial values of alpha 1, alpha 2s are given. Initial values of beta is also given. So you need to convert it into Z domain. So the conversion is already done. So you need to first find out the derivatives of this function, dg by dz1, dg by dz2, dg by dz3. Now once we have this three, we can easily calculate the k value. Now once we get the k value, so we can find out the alpha 1, alpha 2 and alpha 3 value. Now, once we have the alpha 1, alpha 2 and alpha 3 value, we know how to find out the beta. You just need to put all these in your equation of this. Now, once you have put all these things in that equation, you will find that beta is equals to coming as 3.03. Well, now let's solve another problem. Here, actually the limit state is given and the covariance. This problem is also, we have also solved it. What you need to do? The eraser is not working actually, so bear with me. So here, like 3x1 minus 2x2 are given, they all follows normal distribution. Covariance is given, so this is the covariance matrix. So to uncouple them, you need to find out the eigenvalues and eigenvectors of this. So using the characteristic equation, I found it out. And once you have that eigenvalues and eigenvectors, you can easily uncorrelate them and find out the eigenvector of the covariance matrix as this. First eigenvalues, find out lambda 1 and lambda 2, corresponding lambda 1 and lambda 2, you need to find out the eigenvectors. So eigenvalues and eigenvectors you all know, I am not going deep into it. Okay, or you can just check it using MATLAB, whatever you want. Now what this problem says, find equivalent normal parameter of a random variable x follows log normal distribution with sample mean and standard deviation are given. And look, the reference point is very important. The reference point is also given. So mean and standard deviation is given. So for log normal distribution, we know we need to find out the coefficient of variation, and coefficient of variation is nothing but sigma by mu. Now once we have the coefficient of variation, we find out the x tilde. X tilde, if we calculate it, it comes as this. Now once we have x tilde, we know what will be the equivalent normal mean, because for the particular log normal case, we have convert this into, like, we have that equation, we sort of this equation here. Look, x minus x star ln x star phi of this. So just equate this using this formula. So x star 1 minus ln x plus ln x star. So you just need to put all these values and equate it. So it will come as 1.922. Now sigma equivalent, you need to calculate in a similar way. You can find it out. Okay. Now here we have another question, like we have, like, I cannot erase it. So just bear with me. A limit state function is given, 3x1 plus 5x2. Two random variable x1 and x2 are given. Covariance are given. Find out the eigenvalue of variance matrix. Eigenvalue of variance matrix. So it's a very simple thing. X1 and x2 are given. So first you need to find out the covariance matrix. So covariance matrix will be nothing but sigma x square by sigma x2 square and the covariance between them two. Now eigen operation, you just need to do the eigen operation. Either you can perform it using MATLAB or construct the characteristic equation and find out the lambda value. So here the lambda 1 and the lambda 2 are 3.3 and 11.58, right? Simple problem. Okay, that's all for today. So if you have any doubt, you can ask me, or I will just upload it and we will meet next class. What you need to do, you just go through that function files, put or check line by line whether you are getting the same results or not. I think Onassis sir, make these function files in a different way, in a- call them in a different way. Have you gone through the videos, Abdul? Okay. So Bob, is there any question from your end?
No, it's fine. I just have to get sit down and then go through the function files and then
Yeah, you
um
need to go
NLP files.
through them. Yeah, and that function files and the codes I have already uploaded, but before that you just need to solve it in pen and paper. Okay, now I think you get the concept. Okay, how we are solving the problem and why this problem is important, for what we are solving, to get some reliability based on, to quantify some uncertainties. Okay, if you do like that, you will get this kind of probability of failure. You will do like that, you will get this kind of probability of failure, and so on and so on. Okay, so you just go through the examples. I hope these examples will help you to solve the assignments here. And rest, for the learning purpose, you go through that function files of Rackwitz and Rackwitz-Fiessler algorithm, and solve different kind of problems and check whether you are getting the same values, same design points or not. Ultimate goal of this Rackwitz and Rackwitz-Fiessler algorithm is to find out the final design points corresponding to some, probability for failure and some beta, so that we can ensure, okay, if randomness is there, we can counter the randomness up to that certain values. Okay. Okay, then
All right. Do,
yeah.
do do you have any material that can help me with the MATLAB? Any book or anything that
Yeah, you
can
can
that has.
okay. For the basic MATLAB, you can have different kind of tutorial books. Yeah, yeah, these are available on online. Okay, I will give you one book that covers like the whole MATLAB thing from the basic. But actually,
All right.
yeah, just the you just what you need to do is you just learn the basic from any kind of you search for MATLAB basics, you will find a hell lot of videos in the YouTube. But just the basic, you just need to learn. Like MATLAB is vast. Whatever you need to find it out for your purpose, you just need to stick to it. Okay. So basic
Yeah.
commands,
Yeah.
you just find it out in like doc. That command you will get it from here. Like all the commands we cannot remember. I myself also can remember the commands. I just look for it. Okay, I need to do that operation here. Okay, these commands will do that. Or what is the command format, that I just search for it and I get it. Like doc of this, you will get all of these things. Like anything I have used here in the function file. If you feel like what is that thing, you just like doc here in the command window, doc or help,
Mhm.
that both thing will give. Like doc anything, doc of like solve command, doc of any command I have used, you just write it down
Oh, okay.
and you will
Okay.
find it out. Like doc of cdf, I am using cdf command, so one pop-up window will open and yeah, look, the cdf of this, pdf of this, every command are there. So you just need to
Oh, wow.
learn the basic part and then you will get the commands out of here. But the logic flow, okay, after which I need to calculate this, after which I need to calculate, like eigen command, you don't know about eig command, here we have used the eigen command, so just write it down here, like doc eig, it will give you, look how to perform the eigen analysis. E is equals to eig a into or aig,
Wow.
everything you will get from here itself. They have provided all the thing, but you need to know where we need to use that commands. If you forget the command, just stop
Yes.
and write it down, it will give you. Or help command will also give you the same thing. Okay, so anything
Good.
here,
Very good.
at any line, if you stop anywhere, like why I am used this, like here VPA, I have used that VPA command. You don't know VPA, just copy it here and like look for doc or help, they will provide you. Yeah,
Okay. Okay.
so
Okay.
you can
Okay.
check it.
Because that was one of the things. Yeah.
Yeah, so that's why I'm telling you, don't need to go for MATLAB coaching or tutorial from the basic to that. You just need to learn the directories, the workspace, and the logic, what the editor do, what that command window do, what the function file, or what the functions we can call, whom we call the function files. Like function files we can directly run it, these function files we cannot run the function files directly, these are to call them. From where we can call this, from new, I cannot run the function file because I need that input
Uh,
to run them. So from here tutorial 5 I am running the code. Okay, this is the base
okay.
script and I am calling it from there. Okay.
All right. Thank you very much.
Okay. Okay, then so let's stop here and we will meet on the next class. Okay, till now, if you have any doubt, so summarize them and ask me on the next class, or you can mail me. Okay, thank you.
All right. Thank you. Thank you.